quickly go over this content. Concept of empirical formulas. It is the fully reduced whole number ratio of elements within a compound. Okay, so let's take a look at two formulas. Sodium chloride, magnesium chloride. What is the formula for sodium chloride? What is the formula for magnesium chloride? MgCl2. Why did the 2 show up? Balance. We had to balance out the charges on the cation and anion within each of those compounds. Okay? These are technically empirical formulas, though it doesn't really apply nicely to ionic compounds. Okay? And the reason why it doesn't is in ionic compounds, you always provide the reduced formula. Right? Because if I actually looked at sodium chloride, I'm probably not looking at a single atom of sodium and a single atom of chloride. I'm probably looking at closer towards a mole of them. Or maybe if we're talking about just adding it to, your dinner, maybe it's a little bit more like 10 to the 10th. Okay? That amount of sodium and chloride atoms is insanely tedious to write down. Okay? So we don't reference it as atoms. Okay? What numbers did we write next to the sodium and the chloride in the formula?
Invisible 1.
Invisible ones. What are the units on that invisible 1? Okay? We could do atoms, but again, we aren't going to measure an individual atom. So a more general term would be to use parts. Right? It's a large number. If I have 50 billion sodium atoms, I'm going to have 50 billion chloride atoms. The exact number doesn't matter, but the ratio between those is very, very important. So we could use parts, and parts would work great if we were a bartender mixing a drink. We're not. We're chemists. Okay? So what unit do we use? Moles. We don't use grams because now grams is a measurement. That's not a part, that's the mass of a part. Okay? So what we're looking at is moles in our empirical formulas. Okay? It could also be molecules, but again, or atoms, but again, that's too small of a system. So what we're looking at is moles. That gives us mole ratios from the formula, which is fantastic. Okay? Kind of makes sense? For an ionic compound, that as an empirical formula is a little bit nonsensical because there's no way I'm going to write sodium 10 to the 10th for the chloride. I'm always going to write it as the reduced ratio, right? When we move to the magnesium and chloride, it's still MgCl2. I would never write Mg2Cl4 because all I'm doing is now providing a scale up of the official formula. Does that make sense? Okay. So with an ionic compound, we don't refer to them as empirical formulas. We refer to them as formula units, which is really just another way of saying molecules. Okay. So it's a more accurate way because they're ionic. Okay. Empirical formulas are primarily created for molecular compounds. And I just erased the thing that I was going to talk about. So let's take a look at the molecular compound benzene. And for those of you freaking out and being like, oh my God, I have to be able to draw benzene. No, you do not, because this is not an organic chemistry class. Okay? But you should be able to interpret what you see. That is the compound benzene. If I was to draw out the compound of sodium chloride, all I would write would be NaCl. If I look at a bunch of sodium chlorides, they alternate out. Notice how they're alternating. Sodium to chlorine, sodium to chlorine to sodium, chlorine to sodium, chlorine to sodium. There's a very regular pattern behind that. That regular pattern comes from a difference in electronegativity. Test question. Okay? That difference in electronegativity generates a formal positive charge on sodium and a formal negative charge on chloride. So our ionic compounds carry a very regular pattern because we're trying to neutralize that charge. By aligning those charges with each other. When we move to a compound like benzene, what's the difference in electronegativity? The difference in electronegativity between carbon and hydrogen is very, very small. Okay? And if you watch the play posit, it is so small that we reference that as a non-polar bond. There's no charges associated with it. Okay? If there's no charges associated with it, where would I draw the next benzene molecule? Well, it's not going to get connected to this at all. They're independent systems. Benzene is now going to be a collection of molecules that are all independent of each other. Sodium chloride doesn't have independent molecules because they're all ionic. Okay? So they're both reducing down to the same basic idea, the fully reduced ratio. The question becomes is which is more useful? When we're taking a look at our sodium chloride, our fully reduced ratio is NaCl. What is our fully reduced ratio for the benzene? C6H6. Is that a fully reduced ratio? No, I could divide everything by 6. So the empirical formula for this is C1H1. I'm getting the same basic information as the sodium chloride. Okay, so what we're trying to do is figure out that minimal amount of what those pieces are. In sodium chloride, that's great. We now have a reduced ratio. We can see how that would scaffold out. Would I be able to do that with C1H1? Okay, no. I wouldn't be able to build it like NaCl, okay, because I don't have those charges to align them. Okay, and in fact, when I put them together, they don't go together to alternate out. We get this larger structure. Okay? So why would I look at an empirical formula? It gets me parts. It gets me some information. Okay? And in old school chemistry, when we didn't have advanced technologies, an empirical formula gave us something when we had nothing. Now that we have better technologies, when we run our technologies through it, we end up not with an empirical formula, but with a molecular formula, which is the exact scale up for our molecular compounds. Okay? But because of this artifact of the history behind it was exceptionally useful, it is shown up in our textbook, and it's now something that you have to continue to learn and process. Okay? What is that process? We actually already covered it. What is the unit on the 1? Moles. What is the unit on that 1? Moles. What is the unit on that 6? What is the unit on that 6? Moles. Everything that you're doing in your calculations is just saying, well, I know what the unit is from a formula. Take whatever information you're given and put it into that information or put it into that unit system. Okay? So let's go ahead and take a look at an example. We'll come back to that. An unknown compound of radium oxide. So right out of the gate, we're going to question this. What is the issue with looking at radium oxide? What is the symbol for radium? Ra, fantastic. Way to break down the name of radium and come up with a wild guess. And it happened to be correct. What is our symbol for oxide? O. What is the problem with this particular formula if we're going to talk about empirical formulas? It's ionic. And because it is ionic, you can now apply what you know about ionic charges. And those ionic charges tell you radium is a +2. Oxide is a -2. So our formula becomes RAO. We haven't even read the entire sentence, and we already know our answer.
What? Oh.
That was a pretty stupid question. Okay? That said, I'm going to make you do all the work anyway. And by make you, I'm going to do it. Okay? So what did we say was the information? So if we're trying to find an empirical formula, what I'm being asked about is how many RAs, or radiums, and oxygens do I need to combine? I need to know what the X is next to radium, and I need to know what the Y is next to the O. Why Y and not X?
It's not the same variable.
We don't necessarily know that those numerical values are the same, right? So we need to make sure we vary that. Okay? So I need to figure out what those are. Okay, so let's go to the question. The question says that we have 0.726 moles of radium. What was the X supposed to be? Moles of what? Radium. So right there, what do we know? X is 0.726.
We'll put moles.
Okay, we can put moles. I'm okay with that. So if we were to write out our formula, we would get Ra 0.726. Why are you giving me a funny face?
If you reduce it, then you have 7/10 of radium.
Okay. When we're looking at our formula here, what can you tell me about the numbers that show up?
It has to be a whole number.
They have to be whole number integers. Is it a whole number integer yet? No. Okay. So that's not going to be my final answer, but it's getting me towards that process. Okay. And remember, it's not just that it's a whole number integer, it's a whole number integer ratio between the two. Do I know what y is yet? No. So what do I need to do? Figure out y. So what is y in this case? Y needs to be moles of oxygen. What information do I have? I have grams of oxygen. Is grams of oxygen the same thing as moles of oxygen? What do I need to do?
Figure out how many grams are in 1 mole.
I need to convert grams to moles for oxygen. Where would I find the information that relates mass and moles? The periodic table. And the periodic table tells me
1 mole, 16 grams.
1 mole is 16 grams. So now what can I do? Solve it. 12.3 divided by 16 is 768. That's fine. Far enough with me. We'll sort of cross that bridge in a second. Okay, which means my formula then becomes Ra 0.726 O 0.768. Is that a ratio yet?
It is, but it's not reduced.
It's not our reduced ratio. Our ratio needs to be whole numbers. We don't have whole numbers yet. So what should we do?
Make 1 a whole number.
The least one.
How can I make one of those a whole number?
Divided by the least.
Divide by that number. I'm going to pick the smallest number, 0.726. And my formula is going to become RA 1 O 1 and change. Whoever has a calculator can run that. 1.0 something, I think. 0.5.
1.058.
Okay. What I've now discovered is my empirical formula. Yes, you'll note that I have some change out there. What can we do with that change?
Erase it.
Get rid of it.
We can get rid of it. Okay, why? Because it's close enough to 1. What is close enough? Pretty much 1.0 is, regardless of the numbers after it, it's close enough to 1. Okay? What if you don't come out to an absolutely whole number? What if instead of being 1.0, It's 2.0. It's 2. What if it's 2.5?
2 or 5.
So it's 2 or a 3. Now we're confused. 2.5 is coming out at a fractional value, at a half value. How can I get rid of that half?
Double the number ahead of it.
Double it. Double everything, and now you've gotten rid of that half. Okay? That's the basis of our empirical formulas. You're just trying to establish the mole ratio. Kind of, sort of? Okay. As far as how this question can get asked, okay, so here's our steps. Convert your units to moles for each element. Okay? Sometimes it's outright moles. We did that with the radium. Was it outright moles for the oxygen?
Nope.
Nope. So what did we have to do?
Make it mole.
Convert grams to moles. How do we do that? You use the molar mass. Okay? Sometimes they won't give you grams. They'll give you a percent composition. Percent. What does that mean?
Parts out of total.
Parts out of 100. That's why it's cent in percent. So what we can go through and do is assume we have a 100-gram sample. What does that do? It gives me the grams of each of my substances. Now that I have grams, convert to moles. Okay? Once I have the mole values, I will now divide all the mole values by the smallest mole value. Okay? And then round or multiply all values until I get whole numbers. There's my empirical formula. So there's your process steps. Kind of make sense? Molecular requires knowing your empirical formula. And more importantly, it's going to require knowing the molar mass of the empirical formula. And that tends to freak people out at first. They go, oh my gosh, how would you figure out the molar mass for an empirical formula? What is the molar mass for Rao? Good. We saw some people looking at the periodic table. Radium is
1.
okay. It says 226. Oxygen is 16. What do I do? Add them up. I now have the empirical molar mass. Okay. The next part to solve this is I need to know the molecular molar mass. Okay. We're not looking at a question yet, so don't stress about that. Okay. And I would take the molecular molar mass and I would divide it by the empirical molar mass. The answer I'm going to get is a whole number integer. That whole number integer is how many times did the empirical mass fit into the molecular mass. It's telling you how much you need to scale by. Kind of, sort of? Okay. So, an unknown sample. Yeah, we're going to jump to this one. Damn it. An unknown sample was found to be composed of 24 grams of carbon, 2 grams of hydrogen by elemental analysis. What's the elemental analysis? It's the experiment that was done to determine those numbers. Don't stress about it. Okay? What is the compound's empirical formula? Okay? So, right out of the gate, what are we trying to figure out?
The compound.
Carbon, X, and hydrogen, Y. Z, way to be difficult. Said what? Oh. Okay. So X, what are the units for X?
Grams.
Try again. I want moles of carbon. What was I given? Grams of carbon. How do I convert 24 grams of carbon into moles of carbon? And I would get 2. For Y, what am I, you had to do Z. For Z, what are we trying to get?
We're trying to get
Moles of hydrogen. What was I given? Grams of hydrogen. How many? How do I convert that into moles of hydrogen? I'm going to divide it just by 1, and I will get 2. And yes, for those of you doing the math, yes, sig figs, yada, 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 it rotates, whatever. What is our empirical formula? CH. Okay? Our empirical formula must be the reduced ratio. If we look at what this is going to produce, I'm going to get C2H2. Is that a reduced ratio? Nope. I can divide them both by 2, and I would get 1. My empirical formula is CH. Okay? Just because I've yelled at some people for it, you'll notice that I've done a run-on sentence. Okay? Just so you know. Okay? For those of you freaking out, what the hell are you talking about? Don't stress about it. It's not a big deal. Follow the pattern, you'll get the answer. Okay? Make sense? Okay. So we're going to take this exact same compound. Okay? So our empirical formula was CH. So if we take that exact same compound, okay, and I now find out that compound has a molar mass of 78 grams per mole. Okay? What is the molecular formula? Okay? What were the steps that we said to go through and do? CH, what's its empirical molar mass? What is it? 12 plus 1 equals 13. The molecular compound has a mass of 78. So what did I tell you to do next? Divide it by 13. This tells me nobody's done your, multiples of 13. It's 6. Exactly. Okay. What does that mean? That means my molecular formula is C6H6. Miraculously, it came out to be the exact same formula that we talked about earlier with benzene. It's C6H6.
Wow.
Okay? Yes?
Earlier when you did the benzene one, you took C6H6, reduced it to C1H1. Is there a reason that you left the ones in there?
No, it was just to emphasize that there are technically ones in there.
Okay,
That was
so
it.
it's not like if you reduce it from 6 to 6, you leave the ones to denote that it was reduced?
No.
Okay.
Okay? Do you have to do it this way? No. You do need to at least figure out the empirical molar mass is 13. Okay? And that's usually where some people get something. They go, I don't know why we did this division. What this division was how many times does the empirical fit in the molecular? If you can't figure out that math or understand why we're doing that math, that's okay. Because there's what I would argue is a brute force method to this. Okay? I don't know how to do that, but what if it wasn't C1H1, it was C2H2?
It would just be 24 plus 2 equals 26. And then you'd do 7.
Now, does 26 equal 78? No. What does that mean?
Keep going.
This is wrong. So now what should you try? C3H3, which is going to get us 36 plus 3, which is 39. Is that equal to 78? So that is also wrong. So now what do you do? Let's try C5H5. 5 times 12 is? 60 plus 5 gets you 65, which means?
That's wrong.
It is also wrong. So now what you do? Oh man, I'm still short, so I'm going to add another 2. So I'm going to jump up to C7H7, and I get 7 times 12.
You want to do that? You want to do
96,
that?
96, right?
It'll add up to
96.
It's 96.
The total is 91.
84?
Is it 84 plus 7?
Bro, it's 84, bro.
I don't remember 84 being in my multiple.
Yeah.
Is it 84?
Yeah. 12 times 9 is 84.
93. Is 93 the same thing as 78?
Hell no. It's way
No. What does that mean?
91.
What does that mean?
6.
We went too high, so
4 each.
You go back to C6.
so now we go down one, and what do we hit?
Must be 6.
C6H6. Would that equal? Does that work? Yes. Is that tedious? Insanely. This is why we show processes to solve things that show those patterns. Does that make sense?
Of course.
Okay. So when it comes to empirical and molecular formulas, I would argue you should just memorize the process and be done with it. Okay? They don't show up very frequently, and ultimately the point of them is trying to get you to recognize what those numbers mean in a formula. So when I say H2O, what does the 2 mean? 2 hydrogens. Did you know that before we did this?
Yes.
Then why are we doing this? I agree.
More questions for the final.
More questions that we could possibly throw at you during the final. Yes. Okay? So, no. Sorry, that was an old for the exam 3. So, new content for exam 3, we already talked about those. Those are all big things that you need to know for the final, because you will see the same types of questions show up. Okay? So that is important. You are welcome to take pictures. You are also welcome to open up Canvas where it says files, where it says Chem Lectures, and download Unit 3 lecture. Just for... Push your button. Okay? Our conversion factors and where to find them. Just checking if you want a picture. Now's your time. Okay? It's just addressing where that information is. You need to know where that information is. Okay? So if you're having a hard time remembering, look at these. Okay? That's one of the important things in chemistry. How do we find where that information is? How do we decode that information? Conversion factors, we've got measurements and substances. How we can move through it is dimensional analysis and recognizing how to do each of those steps. Okay? I don't find this one as useful, and I'm tempted to delete it because I just don't like this slide. But I built it, so I feel kind of bad. Okay? Limiting reactant percent yield, we threw that one at you. Did anybody attempt it? Did you get it right? Cool. This was off of the last slide deck. I said you should be able to go through and do it, and if you can do this, you've got pretty much exam 3 in the bag. Right. I don't know what the answer is off the top of my head, but I do remember there's a lot of stuff you have to know to be able to answer that question. Okay? So it is a very good review question because it covers all of the bases. Can you expect to see something like this on the final? If it's a multiple choice test, okay, the whole point is to be able to test, do you know the competencies? When you look at this, these are all the things that you have to know to be able to answer this question. Are those all one competency? No. We've got nomenclature, we've got percent yield, we've got limiting reactants, we've got conversions. There are so many different things being tested in this one question that when you get it wrong, what can we learn from you getting it wrong? Very little, okay? Because there's a lot of things that could have gone wrong within that question. Okay, so when we think about multiple choice questions, multiple choice tend to target one concept. This kind of question is perfect for a show your work. Because when you show your work, I can see where you're failing in that process. Okay? Which is the exact system on where this would have shown up in exam 3. It wouldn't have shown up as a multiple choice because I can't tell what it's testing on. Does that make sense? So when you're thinking multiple choice for writing an exam, if an exam is written well, it's targeting only 1 to 2 concepts. If it starts targeting more than that, we can't tell why you're getting it wrong. It's not a useful question. Does that make sense? So, our real leftovers. Here's some fun stuff, so let's get away from the math. In fact, I don't think we're doing really any math for the rest of the semester. So yay, no more conversions. If we were to balance this question, as it's written. Can you balance this? Okay, how would you balance it? You need a 2 in front of the H. Is it now balanced? You get to decide. You really need to be able to look at something and be like, yes or no.
Yeah.
No? Why no?
Well, look. ZN says +2, that's charge.
Zinc changed. It changed its charge. So what happened to the zinc in the process of this reaction? It lost 2 electrons. Are electrons matter? Yeah. So can I have just electrons disappear into nothing? No. So you may have a very valid reason for why this reaction is wrong as written, because we've got zinc losing 2 electrons. It can't just do that. What happened to the hydrogen? We went from H plus with a +1 charge to what? For the H2 with what charge? A 0. Which means what happened to our hydrogen? Went from a +1 to a 0. It gained 1 electron. Whoa, you said 2. What 2?
There's 2 hydrogens.
There are 2 hydrogens. So in the overall reaction, each hydrogen gained 1 electron, but there were 2 hydrogens. Did I need that 2 there? Yep, because it's what's balancing the electrons that I can't see. Did I have to look to see those electrons? Did we place that 2 before or after we looked at electrons? Before. Did I need to look at electrons to put the 2? No. Okay? So the equation is balanced. There is some weird oddities with that charge that might make you panic and inhale a little bit. That's okay. Break it down. It did actually balance out. Okay, but it wasn't necessary to look at those charges. And officially, they aren't charges. What are they? Oxidation states. Okay? So let's take a look at another one. How about this equation? Does this one look balanced?
Yes.
It looks balanced because there's 1 tin and 1 tin, 1 iron and 1 iron. Okay? Is the charge balanced? No. What does that mean? Somehow in the course of this reaction, an electron has either been created, right, or it's been absorbed from nowhere. That's a problem. I can't create that matter. And electrons aren't just allowed to flow off into nothingness, because if they did, when we walked around, what would we feel? Electric shocks from the random electrons floating around. They don't just float around. They are associated with an individual element. Okay. How do we do this? And that's the point of balancing our redox reactions, is we need a process to go through and deal with this. Okay? What we could try and do is the breakdown that we did with the zinc and the hydrogen, and that does become more difficult to be able to process, but you could do it. Okay? And you might say, well, those numbers are too high. We aren't concerned about balancing out the numbers. What are we concerned about balancing out? The electrons. We haven't identified the electrons. When I go from tin plus 2 to tin plus 4, what happened? I lost 2 electrons. Yeah. What happens when I go from iron plus 3 to iron plus 2? I gained 1 electron. The electrons aren't balanced. How do I balance 2 and 1?
Make 2 irons.
I need 2 irons to react across. Okay? So that now the electron transfer balances out. Make sense? Okay? This format is one way to approach it. There are other ways to approach it, and what we're going to walk through really quickly is the half reaction method for balancing it. And as a half reaction, what we're going to do is break apart the equation that we're looking at, and we're going to split it to each half. Okay? When we looked at this reaction, One species gained electrons, one species lost electrons. So what I'm going to do is look at the half of the reaction that gained electrons, and I'm going to look at the half of the reaction that lost electrons. In that process, I will see that I went from iron plus 3 to iron plus 2. Is that equation balanced? No, why not? The charges don't balance. Now I can add electrons. Because I'm only looking at half of a reaction, I can add and remove electrons. They end up being a way to kind of tally the reaction process. So now the question is, where should I place that electron? When in doubt, yes, there's only two places the electron can go.
On the product side.
On the product side is one of them. Do the charges now balance? What is the charge on the left-hand side of that reaction arrow? A plus 3. What is the charge on the product side? Plus 1. It's no longer a plus 2 because I also have an electron in there with a negative charge. That cancels one of those. Does plus 3 equal plus 1? No. What does that mean? The electron was placed on the wrong side. So what should I do? Put it on the other side. Okay? Don't put it on the right side. Put it on the correct side. Okay? Is our equation now balanced? Yes. So let's take a look at the other half of the equation. 10 plus 2 to 10 plus 4. Is that equation balanced? No. What do I need to do? I need to add electrons, right? Okay, I added it on the reactant side before, so let's go ahead and add it again on the reactant side. I would be plus 1 to plus 4. I got further from them balancing, which means, so eloquently put, I was a stupid dummy. And I should place the electron on the other side of the equation. Is it balanced yet? No. I need 2 electrons to balance it. Yeah? If I added these 2 equations now, the one electron would cancel here and cancel one of those. I would still have an electron left over. Am I allowed to have electrons as a product in an overall equation? No. So what I now have to do is alter these equations to ensure that when they are added, the electrons entirely cancel out. So what is the lowest common multiple between 1 electron and 2 electrons? 2. How do I make a 1 into a 2? Multiply it by 2. Okay? And when we're talking about multiplying it by 2, we're multiplying by 2 the entire expression. Which means, yes, I will have a 2 in front of the electrons, but I will also have 2 irons and 2 irons. Now when I add it up, the electrons will cancel because they're on opposite sides of the equation. For those of you a little bit panicked about that, let's take a look at this expression. What does x equal? How'd you do that? The y's were the same on both sides of the equation, so I could subtract them and they canceled out. We're doing the same algebra stuff that we've done in math, just with symbols. When we add up our equation, what do we get as an end result? 2 iron plus 3 plus 10 plus 2 plus 2 Fe plus 2 plus 10 plus 4. If we were to verify that we indeed balance this, do we have the same amount of irons?
Yes.
Same amount of tins?
Yes.
Do we have the same charge?
Yes.
All right, let's check that. I have a plus 2 from the tin. What do I have from the iron? A plus 3, but there's 2 of them, which means the total charge on the left-hand side is?
8.
Let's go to the product side. What do we have? Does my charge balance?
Yes.
Yes. What does that mean?
Balance.
The equation is balanced. Kind of makes sense? If you have to move into 151 and 152, you will see balancing redox reactions with the half reaction method. Okay? There are other ways to go through and balance them. The half reaction tends to be the simplest and the most logically organized so that you minimize mistakes. Okay? Questions about that? Okay. The rest of these slides that I'm now about to whip through were all done before I could write on the screen. Okay. So if you wanted some practice, you could go through and try and balance this last one. What do you guys think? Is it worth it to you?
Yeah.
Okay, balance the last one on your own.
Is it easier?
Okay, the exact walkthrough on that, kind of up to you. If you want to decide, you can come talk to me about that. I did just walk through it individually with one student. Was that helpful?
Yeah.
Okay, just checking. If it's not helpful, I want to know so nobody else talks to me, right? Okay. All we're trying to do is figure out what that half reaction is, what those pieces are. Once we have the half reactions, now we can go through and balance them. So let's take a look at the black one. Is it balanced? Obviously.
Yes. No, we had 2 hydrogens.
We need 2 hydrogens. Is it now balanced?
Well, besides the electron.
Besides the electrons. Okay, so where should the electrons go?
I have no idea.
What is the charge on the left-hand side of the equation? So when I'm saying charge, want to go over here, what is the charge?
+1.
I have plus from the hydrogen, but there's 2 of them. And I have 1 nitrate that's a -1. My overall charge is +1. What is the overall charge on the product side of the equation? 0. There's no charge. Does +1 equal 0? No, which means our equation is not balanced. To balance it now, I need to add electrons. Where should I add electrons? If I don't know, I'll add them. There was a suggestion to put them on the product side. If I did that, 0 plus a -1, and I would get -1. Is +1 equal to -1? Should I have placed it on the product side? I should add an electron to the reactant side. Now do the charges balance? Yes. Now that we've got our first half reaction done, we can move to the second half reaction. Copper to copper +2. Are the elements balanced? Yes. 1 copper, 1 copper. Is the charge balanced? No. What do I need to do? I need 2 electrons added to that one so that the charge balances out. Okay. If I added these 2 equations together, would the electrons entirely cancel? No. One side I have 1 electron, the other has 2. What is the lowest common multiple between 1 and 2? 2. How do I make a 2 equal to a 2? Multiply by 1. So what should I do to the red equation? Multiply by red equation 1, which means none of the numbers change, right? It stays the same. What happens to the black equation? I need to multiply everything through by 2. So this becomes 2 electrons, and it becomes 4 hydrogens, and it becomes 2 nitrates, 2 waters, 2 NO2s. Now I can add my equation together. I would get 4H plus 2 NO3 minus plus Cu plus 2 H2O plus 2 NO2 plus Cu plus 2. Yeah? Okay. So let's take a look at our charges. What part of this is not balanced? Are you saying the charge or the number of elements? Number of elements. How many coppers are there? 1 and 1. How many nitrogens? 2 and 2. How many hydrogens? 4 and 4. How many oxygens? Try again. Try again. Thank you, JC. 6. Other side? 6, 4, 2. So all of our elements are indeed balanced. So the elements aren't the problem. So those of you saying that this reaction was not balanced, it was not because of the elements. The elements are indeed balanced. So let's take a look at charge. What is the charge on the left-hand side of the equation? This brings in a +1 from our hydrogen, but there's 4 of them. Plus nitrate -1, but 2 of them. Copper is 0. Nothing specified. 4 times +1 is 4. 2 times -1 is? What is 4 minus 2? 2. Take a look at the product side. Charge from our water? 0. Charge from our NO2? 0. Charge from our copper? +2. We add all of those terms together and we get? +2. Does +2 equal +2? Yes. Is it balanced? Say that again? Did you say what?
I said wow.
Wow. Okay. For those who being like, well, at least I don't have to worry about that and it can't possibly get worse. It does. Just not in this class.
Next class.
Okay? That would be 152. Is where it gets best. Where it gets worse. Okay? The big part that you need to be able to recognize is what we're falling back on to do this. Okay? Where did charges come from? Electrons and not neutrons. So there again goes all the way back to Unit 1. This is why we built up all the way from Unit 1. Subatomic particles, protons, neutrons, electrons. Neutrons have what charge? 0. Protons have +1. Electrons? -1. So when I see a charge in my equation, it's due to the balance of protons and electrons. It is primarily driven by the number of electrons because the electrons are allowed to change. If I change the protons, I change the element. Sounds like something from Heroes, right? Change the protons, save the world? Something? I don't know. You're probably all too young.
No.
I didn't actually watch it, so it's okay.
The first season was good. After that, it stunk.
Yeah, most people did, apparently. Man, there's a lot of hat tips today. You should be able to go through and balance this one on your own. We're not going to go through and balance it. Okay? Because where I would like to get is something more interesting, which is the types of forces. Okay? The play posit addressed these forces and where they come from. Okay? If you did not watch said play posit, you will not be able to answer these questions. Okay? And everything thereafter will be completely unknown to you. Watch the play posit. An ionic or electrostatic force comes from what? How would I know I have an ionic or electrostatic force? I have an ionic bond. How do I know I have an ionic bond? Okay. So one of the extra definitions between for an ionic bond is a very large difference in electronegativity. And you can quantify it. The problem with quantifying it is that you would then also need to be able to know all of the electronegativities. And since the majority of us, and probably all of us, have not memorized more than 5 electronegativities, I think I've got 3. 3 is about all I got. Okay? Then using electronegativity to differentiate the different bond classes is a horrible idea. Okay? How do I know I have a London dispersion force? Where does that come from? This is a nonpolar covalent bond. I know I have a nonpolar covalent bond because
Perfect sharing of electrons.
there's a perfect sharing of electrons. How do you know you have a perfect sharing of electrons?
Same atom bound with the same.
I'll accept that. Same to same and carbon to hydrogen. Okay? That perfect sharing is because your electronegativities are the same. Okay? Again, there's a threshold behind it. How do you know you have a dipole-dipole? Okay? And we could reference it as a polar covalent, and that is the more traditional answer behind it. But then how do we know what a polar covalent bond is? It's nonmetal to nonmetal. That's the same as a nonpolar covalent bond.
Not a perfect
Okay.
sharing of electrons.
And it's not a perfect sharing. So the opposite of a nonpolar covalent bond. So all of the definitions that you've provided are pretty much check to see if it's ionic, check to see if it's nonpolar. If it's not one of those, it's everything else. So we're now looking at the dipole-dipole force. You'll notice that there's 4 things up there. I can't just say everything else because it could incorporate hydrogen bonding. Hydrogen bonding is a subcategory of dipole-dipole. Okay? So the first thing I would have to establish is, do I have a dipole-dipole force? If I do, then I can look to hydrogen bonding. In that second check, what do I need to verify?
H is bound to chlorine, oxygen, or nitrogen.
Okay? Rule 1, it should probably have hydrogen. Use the language to help you solve. Okay? And we could go with a couple routes. You could remember it as NOF because you've had enough chemistry. Or you could remember it as FON N because chemists always want to have fun. Okay? What is the characteristic of fluorine, oxygen, and nitrogen?
They're super electro.
Those are the 3 most electronegative elements. Being bonded to hydrogen being one of the least electronegative, meaning we get a very large difference in electronegativity. So large that we call it hydrogen bonding. It ends up equating in strength to an ionic bond. Okay? And that is an exceptionally strong interaction. This is why biologists reference it all the time, usually incorrectly, but that's biology. Okay? So what you need to be able to do is to be able to identify your 3 bond classes and how those bond classes manifest into intermolecular forces. Okay? And if that wasn't enough, what you end up having to do with that is apply that information to phase transitions, vapor pressure, solubility, reactivity. Virtually what we've summarized right here on the right hand, those kind of questions, are all based off of intermolecular forces. Virtually all of chemistry is in this wheel. Okay? Which is pretty shocking if you ask me. What we're talking about, everything we've talked about this semester, is summarized in that slide and that distinguishing between those. Okay? And it ultimately is coming down to how we quantify each of those pieces. So we're going to walk through real quickly how to interpret this. What we're looking at is an attraction between 2 things. Any 2 things. Okay? In chemistry, those 2 things are atoms. Those don't have to be individual atoms. They can be attached to a molecule. But I'm concerned about their interaction with each other. Okay? If it is a very weak interaction, like they don't care about each other, we're looking at a London dispersion force. Minimal interaction. Why are they minimally interacting? because their connection to their other structures are covalent, meaning we get virtually no charge. If there's no charge, there's nothing to interact with outside the molecule. So a molecule that is very strongly bound has very weak interactions with other molecules. That's what that means. As I increase the strength of attraction between those two molecules, okay, I'm now changing the force. And I can call that a dipole-dipole force. Well, where did that force come from? Okay. That came from a polar covalent bond. Those two atoms' connections to the rest of their environment was weaker, which caused a partial charge to build. That charge now means they need to seek somewhere else for stability. So we get a stronger attraction. As we continue to polarize the molecule, we get stronger and stronger interactions between those atoms. They eventually reach a point where those interactions are now so strong between those two atoms that what did they say to their respective starting partners? Screw you. I don't need you anymore. And so they break away from their starting structures so that they can interact strongly with each other. That breaking is now the breaking and ultimately the differential between an interaction, weak interaction, a force, and a strong interaction, a chemical bond. That differentiation is very, very subtle, and it passes through our ionic interactions. As we continue to make it stronger and stronger, we continue to move around our curve. Okay? So what you need to be able to do is to interpret what are the bonds, what are the forces, and then how strong those forces are and how they apply to all of those things we've talked about. That is where we will pick up on Tuesday. I wish you all a happy Thanksgiving.
Thank you, Mike.
I'm thankful that you are all still here. And we'll see you on Tuesday.